course, Discord is downloading 8 updates on my laptop naturally. Abby has messaged me. We can hear and see. Okay. Abby tells me everything's good and all problems are on his side, which is a shame. But all right. So I'm just going to pull up my notes for today and then we'll get going. Thank you for your patience. All right. Let's see. It's going to be, where are these notes? Here we go. That's what I wanted. Okay. So, yeah, today we're going to talk about FRI. Okay, this is a hashing-based polynomial commitment scheme. So the only cryptography it uses is hashing. We've talked about a lot of commitment schemes based on elliptic curves, Hyrax, Bulletproof, Story. And we've also talked about some based on hashing. So a quick reminder of what hashing-based ones we've already talked about. So these were Lajero's commitments, Breakdown, Binius, Basefold, etc. Well, sorry, Basefold. Basefold's related to FRI, so let's skip Basefold here. And what were the costs of these compared to something like FRI? So these the evaluation proofs, and I'll remind you what a polynomial commitment scheme is in a minute, but the evaluation proofs are square root n in size about. Okay, and n here is the size of the committed polynomial. So if it's a univariate polynomial, this means like the degree in the univariate case. If it's a multilinear polynomial, this is actually like 2 to the number of variables in the multilinear case. But yeah, it's just like how many coefficients does it take to specify the polynomial? Okay, so these were pretty big evaluation proofs that we saw previously. So that was kind of the downside. So FRI has much shorter evaluation proofs, at least asymptotically, than Lajero breakdown and Binius. But there are some benefits to like Lajero breakdown and Binius relative to FRI. So they generally have a faster prover than FRI. Experimentally, it's often like 10x or more. And something like breakdown can use an arbitrary linear error correcting code. So as we'll see today, FRI specifically is very specific to the Reed-Solomon code. Something like breakdown is not specific to Reed-Solomon. So this can have downstream benefits. This can give even bigger speedups than like this 10x for the prover, and also give you more flexibility in what field you work over, right? Because not all fields are like very nice for Reed-Solomon codes. Yeah, so like Reed-Solomon codes, which are used by FRI, they need an FFT friendly field. So the field has to let you, take a vector of length n and, compute what's called its FFT quickly. And not all fields have that property. And so, like this breakdown doesn't need that. But with breakdown, its proofs are bigger than FRI's, and when you move away from the Reed-Solomon code, concretely, they get bigger yet. So that's kind of the trade-off, is that the proofs here are so big that like no one's really using breakdown today. Even though there are some settings where like really big proofs wouldn't be a big deal. So yeah, trade-offs everywhere. Okay, so FRI, it's very popular. I'd say its main claim to fame is amongst, hashing based polynomial commitment schemes. It has the shortest proofs. Right. And so, it has a reputation of being very fast for the prover. But I actually think that reputation is sort of misguided, because there are much faster things for the prover. So in my view, FRI is actually optimized for verifier costs, not for prover costs. And I've discussed many times over the course of this study group. The fact that I generally think like the most popular techniques and snarks today are over optimized for verifier costs when prover costs are like the real bottleneck. So I won't elaborate on that at length here, but yeah. So this is really what FRI is kind of uniquely good at. And so what is the proof size for FRI? And I'll state this and then pause for questions. So asymptotically speaking, the proof size is lambda up to a constant factor. It's lambda times log squared n. Okay, so this is the security parameter. So think of it as like 128. Depending on certain parameters within FRI, this hidden constant might be less than 1. So this might be less than 128 log squared n, concretely. But in practice, you should think of the proof size as roughly being like 100 kilobytes and up. This is heavily dependent on, I guess, like many things. Depends on how fast you want the prover to be. So if you want shorter proofs, you generally need a slower prover. But you can kind of get around that a little bit if you're using recursion, where you kind of, have a fast prover but big proofs, but then that's not the final proof. You kind of then prove that proof, and thereby shorten the proof a little bit, and then do it again and again and again, so your proofs get shorter as you go, and the prover time is still dominated by the very first proof generation event. It also depends on how aggressive you want to be with security assumptions. And maybe I'll say more about that later. But basically, this 100 kilobytes is only going to be achievable if you're willing to assume that like known attacks are exactly optimal, even though we don't have any justification for that statement, in even the random oracle model and things like that. So that is that is the proof size of FRI, kind of both concretely and asymptotically. There has been some progress in bringing this down a little bit recently. In particular, we discussed this not that long ago. I don't know why I'm blanking on the name. Stir, yeah, Stir. This actually improves this to something like the log squared n turns into something very close to log n, but concretely, it's not a big improvement. I think in the parameter regimes that people typically deploy under, it's not, it's almost not an improvement at all. And in other regimes, it can be as big as like maybe a 2x improvement in some regimes concretely. So this is actually like a very big improvement asymptotically, in my view. like, turning a log squared into a log is like really meaningful, but concretely, kind of we're not quite there yet in terms of it being a big improvement. And there's been some follow-up works as well, which I think is mainly focused on verifier time instead of proof size, like were and others. So yeah, so that's the situation with hashing based commitments and FRI in particular, and subsequent work. Okay, so let me pause here and see if anyone wants to ask any questions. I guess if Abi's having technical issues, I don't necessarily have any way to track what's going on. Okay, I'll just assume no questions. Might be good if Abi's messaging me. Okay, is FRI Binius an improvement? Good. Thank you for that question. So the question is, what's the deal with FRI Binius? And so I'm gonna give two statements about how FRI Binius relates to FRI. Okay, so first let me talk about basefold, which is a predecessor of FRI Binius. So basefold is a multilinear analog of FRI. So FRI is targeted at univariate polynomials. Basefold is targeted at multilinear. Okay, and multilinear is what you want whenever your PIOP uses the sum check protocol, which is of course my how I think PIOP should be designed to achieve a fast prover. So basefold is a multilinear analog of FRI. Okay, and then FRI Binius is like an adaptation of that. Roughly, anyway, I think this sentence is accurate enough that it's a good answer to your question. To binary fields. Okay, so so basefold operates over like an FFT friendly field, where this is referring to FFT friendly field, the same way FRI does, where this is referring to like some kind of prime characteristic. So I don't know if you want to call it like a let's say in a multiplicative subgroup. Apologies for like the technical statement. In a multiplicative subgroup of the field. And these binary fields, when you do FFTs in these binary fields, you work in what's called an additive subgroup. And so, if the FRI Binius folks, they want to work over binary fields because that makes it very fast to commit to small values like zeros and ones. And they couldn't just say, well, let's use basefold, because basefold, didn't work everything out in the binary case where you work in these additive subgroups instead of multiplicative ones. So that's it. So FRI Binius is a multilinear analog of FRI, specifically targeted at binary fields. Hopefully that is a clear answer to the question. Yeah, so the Binius line of work kind of has two different contributions within it, and they're sort of, they go together nicely, but they're kind of unrelated contributions. So one is kind of just like using the sum check protocol to make it very fast to commit to very small values when you work over binary fields, and that technique or result can be combined with any multilinear polynomial commitment scheme over binary fields. But then if you want one with the shortest known proofs, that the one you should use is FRI Binius. Okay. I'll assume there are not additional questions unless Abi texts me. I'm keeping an eye out, Abi, in the Discord chat. So if you want to, in our DM, so if you just want to message me, I'll know there's another question. Okay.
Can you hear me now?
Yes.
Sweet. Excellent. Okay. And you're, yeah, no more questions. Thanks for the patience.
Okay, great. All right, yeah, and that was a pretty good summary of like a lot of what's happened. There's been other works in this domain, like Blaze, by the way, is sort of, Blaze is sort of to FRI Binius as breakdown, is, to like Lahero or FRI or something. But Blaze is trying to use different codes. That's not the Reed-Solomon code. But Blaze is targeted at binary fields, whereas Breakdown was not looking at binary fields. And So, very active area of research, these hashing-based commitment schemes. So a lot, lot to mention. I'm sure I'm missing some very nice recent results here.
Quick question about that. You just mentioned that I think Blaze was like using something different than Reed-Solomon codes. Kind of in that space, like, is there a big variance in like which codes they use? Because I know we mostly talk about Reed-Solomon, and it seems like that's the most common one. Is that accurate?
Yeah, it is the most common one. Actually, it's probably worth a quick review. So I'll answer this question because it's worth reviewing this anyway with this kind of extended answer. I'm gonna review like breakdown real fast. Okay, super quick review. It's good to compare. I think this is this is worth the time it takes to do the review so that we can see how FRI differs from it, and in the process, I will discuss kind of what the trade-offs are of using different codes. Where Reed-Solomon wins as far as we know today, and where other codes can win at the cost of losing on another axis. Okay, so with breakdown. You take the polynomial to be committed and you write its coefficients as like a square matrix. Okay, so it's like if your polynomial, let's say we're dealing with univariate polynomials exclusively today. So if your coefficients are c0 to cn minus 1, you kind of just write the first root n coefficients along the first row, and then the next root n coefficients along the next row. Yeah, and what you do in breakdown is you take each row and you encode each of them kind of independently with some error correcting code. And Lahara breakdown, if you use the Reed-Solomon code, then breakdown is just Lahara, which is a much older paper. Okay, so you encode each row, and then the commitment to the polynomial is just the Merkle hash of the encoded matrix. And then so you just Merkle hash that whole thing. Maybe I'll draw the hash down here. And so this Merkle root is the commitment. Okay, and then the evaluation proofs kind of ask the prover to provide I write this out. So when the verifier wants to know the committed polynomial evaluated at R, sort of what you do. I'm going to wave my hands a little bit, but R sort of determines like a bunch of random coefficients, one per row. So somehow, again, waving my hands, this turns into let's say root n random values, one per row. Maybe today I'll just call them v1 to v root n, and the prover is supposed to send the linear combination of the rows given by these coefficients. So in matrix vector form, that would be if this is the vector v, that would be v times the matrix. So yeah, and so I call this like a random linear combination of rows because v is random. If R is random, then v is random. So random linear combination of rows, like that's what the prover sends to the verifier, and then the verifier wants to make sure that the prover actually sent the requested random linear combination of rows. And so what the verifier winds up doing is like picking order lambda, which is think like 128 or so random entries of this vector that's supposed to be the random linear combination of rows, and confirming what we call consistency. That is, it literally checks, it makes the prover open up M at the necessary columns here to confirm, so the verifier confirms that this vector the prover just sent, I don't know, let me call it U, UI equals, V times M, at, about 128, randomly chosen entries. So these are called consistency checks. Okay. And, the reason the proof size is root n, which is like smaller than n, so it is sublinear and what I would call succinct, but still somewhat big, is because there's like one entry in this vector u like per column of m, and then moreover the verifier is opening up these entire columns, each of which has a number of entries equal to the number of rows. So both of those costs are root n, and you kind of can't change the shape of the matrix to go below root n, because if you make fewer rows, you make more columns. If you make more columns, you make fewer columns, you make more rows. And so costs are minimized when the rows and columns are equalized at root n. And so this random linear combination of rows, today, compared to FRI, people call this folding, which is a term in snark design that's wildly overloaded and used to mean different but loosely related things. So in the context of FRI or breakdown or Ligero, I would call this one big fold, right? So that is we sort of took the polynomial we committed to, which was p, right? We broke it into square root n, rows or pieces. Let me call each row a piece of p, each of size root n, right? And then by taking a random linear combination of those root n pieces, we smushed them all together, right? And that's what people in the context of hashing-based commitments mean by folding, typically. So we took a random linear combination of those root n pieces, to get one piece. Okay, so coming back to Abhi's question, after this whole review, the trade-offs for codes are the following. So basically, these codes have a notion of minimum distance. That's like how close can two different code words be to each other. And so the better the distance of the code, the shorter the proof. Okay. And so code distance, in something like breakdown or Ligero, translates to evaluation proof size, right? So the better the distance, the better the proof size. Okay. On the other hand, prover time is determined by not the code's distance, but encoding time, because the prover has to take each row and encode it, and Merkle hashing time. And Merkle hashing time is itself determined by code word size. Okay, so Reed-Solomon really excels in code distance. So it leads to the if you're applying breakdown, which is just Ligero with a general choice of code, you're going to get the shortest proofs when you do Ligero itself by using the Reed-Solomon code, because Reed-Solomon code has the best distance. Okay, but by using codes with worse distance, we know that you can make the the prover time faster, faster encoding and potentially like shorter code word size. But when you do that, as of today at least, you wind up with much bigger proofs. So Blaze was looking at like a certain coding scheme, to try to get a nice trade-off between prover time and proof size. But the proof sizes in Blaze, I believe, are still much bigger than the proof sizes of Ligero. They both are root n asymptotically, but a much worse hidden constant in Blaze and the code from breakdown and stuff like that. Did that answer the question, Abhi?
I believe so. It was from Zeman, but yeah, that sounds good. And then there's a quick question about the distance kind of between the RS code distance. Like, what does that mean? When you're saying like the distance of the code, you're talking about distance between code words, right? Or like the smallest distance between any two code words.
Yes, exactly. So let's actually just review the Reed-Solomon code real fast, because that's good for discussing FRI anyway. So with Reed-Solomon codes, let's say here's the message to be encoded. And so this message has, say, n symbols. They're just n field elements. Okay, and so let's call them, I don't know, M1 to MN, and kind of different ways. There's different ways of interpreting these symbols as specifying a univariate polynomial. The way that makes the most sense today is as follows. So we interpret M1 as some evaluation of a polynomial. Let's say this is a degree n-1 polynomial. I think it's going to be easier today, maybe to have n+1 symbols. Sorry, so we have that makes the degree n instead of n-1. I think that's just easier to talk about today. So m0 will be interpreted as the evaluation of some degree n polynomial at some point x0. Mn will be interpreted as p at a different point xn. Often, in practice in Snark design today, in FRI in particular, x0 to xn are nth roots of unity in the field. Not all fields have n distinct nth roots of unity, but the ones, so FRI is a little bit limiting in terms of what field you can work over. Anyway. This is one particular choice of these. This is called the interpolating set for the Reed-Solomon code. Okay, and so there's a unique degree n polynomial, with satisfying all n+1 of these equalities. And what the Reed-Solomon encoding of the message is to then provide extra evaluations of the polynomial. So you might add in, p of, let me call it x of n+1 up to p of x of, let's say 2n. There's nothing special about 2 here. And so now, x0 up to x2n would be like 2nth roots of unity in the field. Okay, and the key point is that, in these fields that have n+1 distinct nth roots of unity and 2n+1 distinct 2nth roots of unity, there is, it uses FFTs, but there is an order n log n time algorithm, that evaluates these extra redundant evaluations of p, p of xn+1 up to p of x2n, given as input, this message, which we were interpreting as, p of x0 up to p of xn. So that's called Reed-Solomon encoding. And so what you're doing here is, you're taking this message of length, n+1 in red, and you're adding redundancy to it. And the way that redundancy is added is, again, you're interpreting the message as specifying, all evaluations of a degree n polynomial over an interpolating set, and the redundancy is just adding additional evaluations of the same polynomial. Okay, and I keep giving these very long answers to Abhi's questions, which is, kind of in character, but the question was what is the distance of the Reed-Solomon code? And, there's this basic fact that tells you the distance of the code, which is that any two distinct degree n polynomials can agree on, at most, n+1 points. I always forget if it's n or n+1. I think it's n+1.
If they're distinct, they can only agree on endpoints. If they agree on n+1 points, they'd be the same.
Yeah, two lines that are not the same agree on 1 point. So that's degree 1. Yeah, okay, thank you. To agree on almost endpoints. Yes. Okay, so that directly translates to distance of the code, right? So if you have two different messages, that means they specify two different polynomials. So you look at the two code words corresponding to those two messages, and they're just evaluations of two distinct degree n polynomials, right? So how many symbols can they agree at? Well, they can agree at, so two code words agree at most, n out of they have, 2n+1 symbols, right? So their distance, is what we call about a half, right? And if you increase 2n to 4n, right, the distance would get better. The distance goes to 3/4, right? Because they still can only agree on n points, but now they're on n symbols, but now there are 4n symbols instead of 2n symbols and stuff like that. So, and now you see a trade-off where so if you have 4n evaluation points instead of 2n, it takes the prover longer to, compute the encoding, that is to compute all of these evaluations. And then moreover, it takes the prover longer to Merkle hash all those evaluations because there's more of them. So the prover is getting slower here. I'm jumping ahead with the Merkle hash, but we'll see. Like the commitment in FRI is just to do the Reed-Solomon encoding and then Merkle hash it. So yeah, the bigger you set the number of evaluations here, kind of the slower the prover is to commit, but then the better the distance of the code, which means ultimately the shorter the evaluation proofs. So there's a direct tension here. Like more prover time means shorter evaluation proofs within FRI. Yeah. So did that answer the question
Yep.
as hoped? Okay. Yeah, and so this whole thing about having a code word of length 2n and distance n or 1/2 or whatever, a code word of length 4n and distance 3/4. I think that's actually optimal. I think Reed-Solomon codes are what are called
MDS.
MDS. Yeah, I think that's
Yeah, it
maximum
is.
inseparable. Yeah. So basic. Yeah. So they're kind of the best possible code for proof length, given a particular, like code word size. So, you kind of, in a sense, can't beat them for proof size in something like Breakdown or Laharo. Of course, you could use a commitment scheme that operates from completely different machinery and get shorter proofs. All the curve-based commitment schemes tend to, accomplish that. Bullet proofs is log n proof size instead of lambda log squared n or whatever. But using, these error correcting codes and hashing alone, this is all we know how to do. And then the Reed-Solomon codes have the best distance for a given code word length. So they're going to give you the best proof size, but not necessarily the best prover time. Okay, more questions? Cool. All right. So just pulling up my notes here. So we've actually, I basically just told you how FRI commitments work, but let me just think for a second about what I want to cover next. All right. So yeah. All right. So yeah, let's just dive into it. So let's say I want to use FRI, to commit to, this degree n polynomial P. So what you do is, you take the evaluations of P, over the interpolating set, which in FRI, I think specifically you really need this to be the nth root to unity. There's just kind of no way around it as far as I know, over nth root to unity in the field. What does that mean? That means x such that x to the n minus 1 equals 0. So that is you raise these points, inputs x that are so for each of these points, if these evaluation points, if you raise them to the nth power, you get out 1. Okay, so if we call these nth roots of unity, like I said before, x0 to xn, with FRI, we just, the prover is going to write down these evaluations. Okay, it's then going to, Reed-Solomon encode them. So yeah. So really, so it has to compute the evaluations of P actually over all 2nth roots of unity. Yeah. So let's say 2n. Yeah, and the commitment to P is just the Merkle hash. So the FRI commitment to P is the Merkle hash of this vector, of this vector that just has these 2n evaluations of this polynomial P to be committed. Okay, so that's committing with FRI. Okay, and once you commit, it's like, yeah, the verifier is, in any polynomial commitment scheme, then like ask the prover, hey, v says tell me P of R, and the prover in a polynomial commitment scheme is going to, provide P of R and prove that indeed, this value it returned is consistent with the P inside the commitment. But actually, this is not the way FRI is typically formulated as a polynomial commitment scheme. It's normally formulated as a closely related procedure. So let's get rid of this for now. It's normally FRI, can be formulated instead as what's called a low degree test. Okay, and they're very closely related. In fact, it's known that you can take a low degree test and use it to give a polynomial commitment scheme. But there can be some overheads in that transformation, which maybe I'll say a little bit about later. So right now, let's just forget about polynomial commitments and talk about low degree tests. Okay, so what is a low degree test? A low degree test is saying, hey, imagine you're the verifier who just received this commitment. So this commitment is a Merkle hash, right? And like Merkle hashes are binding. So that means, kind of like inside this commitment here, there is some vector of length 2n. Let me call it, I don't know, W, of length 2n. Okay, now if the prover's honest, so the verifier just knows the commitment. It doesn't know what this vector W is that's inside the commitment. So if the prover is honest, W, just lists, 2n evaluations of a degree n of polynomial. Okay, so what the verifier will want to do, because the verifier doesn't trust the prover, is the verifier just wants to check that that's indeed the case. So W lists all 2n evaluations of a degree n polynomial. Okay, and so roughly speaking, that's what a low degree test is. Now, what's going to happen is the verifier, to enable succinctness, meaning the verifier never wants to take the time to look at every single entry of W because it's huge. The verifier is ultimately only going to inspect a relatively small number of entries of W, which means you can't actually let's say W indeed equals all 2n evaluations of a degree n polynomial, except like one entry is corrupted, one entry is off, right? Like you just can't hope for the verifier to detect the one entry that's wrong if the verifier is only inspecting like a tiny fraction of all the entries. There's no hope. So that's what the test in low degree test means. So a low degree test wants to distinguish two cases. Now the details of this actually won't really matter so much for getting a pretty good understanding of how FRI works. But I will state, what FRI actually guarantees as a low degree test. And then we're kind of going to just wave our hands, I think, for most of the rest of the session. So we want to distinguish two cases. So one is the prover's honest. So that is W is actually all evaluations, over, the relative relevant set of inputs of a degree n polynomial. And the other case is W is far. People say delta far. I always get confused if they say delta far or delta close, and that's annoying. But delta far, for some significant value delta from any such polynomial. Okay, and what delta far means is that like W of xi. Let's put it this way: for any degree n polynomial P, W at xi differs from P of xi, for a delta fraction of xi's. Okay, so if delta is really tiny, like 1 over n or something, meaning W differs from some degree n thing at only 1 or 2 cells, there's just no hope to detect that with high probability without like basically reading all of W, and that would kind of give away succinctness. So we're only can hope to detect that the prover cheated and didn't commit to a degree n thing if what it committed to is quite far from a degree n thing. And it turns out that this is sort of enough for snarks anyway, for reasons I might be able to elaborate on later. Yeah. So that's what a low degree test is. And so, yeah, we're going to formulate FRI as a low degree test. So it's like, again, you imagine you're the verifier, you've received this Merkle hash. There's some big vector of length 2n within the, inside the commitment. And you want to know, is that vector, indeed a degree n polynomial or not? Okay, so how does FRI work kind of pictorially? It proceeds in log n rounds. Okay, and these log n rounds are highly reminiscent of things like the sum check protocol, which also has log n rounds. So it's reminiscent of sum check. It's reminiscent of bulletproofs, which literally actually is sum check in a different guise. So the same kind of technique comes up over and over again. But FRI, of course, that doesn't mean you can just say, hey, FRI is sum check. That's not an accurate statement as far as we know. So I do have to tell you in full detail, like, how does FRI work? I can't just say, oh, it looks a little like sum check, right? So what happens is in round one, the prover is going to take this committed vector W. It's going to cut it in half. Call it W. I'm going to use bulletproof like notation here. WL and WR. Okay, and the verifier, is going to send to the prover a random field element. I'm going to call it R1 or something, and the prover is going to reply with a vector. I guess I'll call it, I don't know, W2, which, if the prover is honest, is claimed to equal something like R1 times WL plus 1 minus R1 times WR. Now, in FRI itself, it won't literally be this. These will not be the coefficients. They'll be kind of different. This is me waving my hands. I think basefold actually does manage to get this to be R1 and 1 minus R1, but they wanted that. FRI itself, it's not going to be, so I'm hand waving here. The actual coefficients are different. I will tell you what the actual coefficients are when I tell you in full detail how FRI works. For FRI are different. But the point is that, like, the verifier is choosing some randomness, and somehow that randomness specifies like a random combination of WL and WR. Okay, so the prover is going to send a commitment to this W2, gets Merkle hashed by the prover, and that commitment is sent to the verifier. Okay, and this W2 now, it has half the length of W. So this is length n, not not 2n, right? So this is what kind of folding means here. We took a length 2n thing, we broke it into two halves, and we collapsed the two halves upon each other to get something of half the length. Okay, moreover,
is NTT applied in each round?
No. So FFTs are only needed to commit. Once you've committed, like, doing this folding procedure is linear field work, because it's like you're taking each entry of W. It's like WL and WR were hard to get. You needed FFTs to get them. But once you have them, we're just taking like random combinations of their entries moving forward. So the FFTs only come in the commit phase, not in this folding procedure. And then another remark there in terms of the folding procedure not being super, super expensive for the prover is often the way FRI is applied is the prover will actually commit to like several hundred polynomials. And then there's a way to apply this folding procedure kind of only once for all of them. And that's another way to kind of keep this folding procedure from being a prover bottleneck. So, I mean, the implementations can be tricky, and this might not be true all the time. But generally speaking, you're going to be reasonably accurate in terms of thinking about prover costs. if you focus on time to commit and not on the evaluation proofs. As things get faster and faster, I think you're going to have to pay more attention to the cost of computing evaluation proofs. But all this Binius and Blaze stuff should make committing fast enough that the evaluation proofs start to really matter. But if you're just looking at vanilla applications of FRI today, I think committing is going to be more painful for the prover than the evaluation proofs. Was that clear?
Yep.
Great. Okay. Yeah, this Binius stuff makes it extra fast to commit to small values, and so it's kind of speeding up the commitments, but the evaluation proofs stay just as expensive and stuff like that. Okay. So so we did this one fold here, but we're not done, right? Like in Breakdown and Laharo, which I reviewed before, we sort of, rather than splitting the committed thing into two halves, we split it into root n rows, each of size root n, and we sort of munged them all together all at once. So that's what I call one big fold. Here we did, we broke it into fewer, bigger pieces and folded the pieces together. But because there were so few pieces and they were each so big, we're not done. We still have something that's only half factor 2 smaller than what we started with. So we're not done. Okay. Now, however, if the prover's honest in FRI, the way this combination is described, and that's why I'm kind of lying here, it's not R1 and 1 minus R1, it's something else. Though, if P is honest, W2 will have degree n over 2 rather than n. So what I mean by this is, the W was all 2n evaluations of, if the prover was honest, of the committed P, of a degree NP over 2nth root to unity. So all 2n plus 1, 2nth root to unity. I hope there are 2n plus 1 root to unity. I always forget if they're 2n or 2n plus 1. So don't judge me if I'm off by 1 here. But anyway, and what W2 is supposed to be is all n evaluations of a degree. So if the prover's honest, this is the case, of a degree n over 2 polynomial, let me call it P2 over nth root to unity. Okay, so if the prover's honest, we've have the length of the vector and we've also have the degree. Yeah, and we've made a little bit of progress because we've have these two things, but n over 2 is still really big, right? So we're not done. So what FRI would do is just repeat, right? So we take this W2, we break it into two halves, W2L and W2R, right? The verifier would pick, I'm going to call it R2, chosen at random from the field, right? And then the prover, computes the folding of W2 with this randomness. So again, I'm waving my hands here. This isn't quite right, but let's say R2 times the left half plus 1 minus R2 times the right half. Let me call that W3, right? And, sends the Merkle hash of that. And again, if the prover's honest, well, so for sure, W3, has half the length of W2, so now that's n over 2. And if the prover's honest, now W3 has degree, what is it, n over 4. Okay. And that's how FRI proceeds. So you keep doing the folding over and over again. And after you've done it logarithmically many times, what you have is this W log n, where, this is a length 2 vector, right? Because we started with a length 2n vector, but we halved its length, n times, log n times, and that should drop the length by a factor n. So W log n is a length 2 vector, but if the prover's honest, it has degree 1. Right, and degree 1 is degree 0. Degree 0. Degree 0 is just a constant. So in particular, that means if W log n is just 2 entries, it's degree 0 if and only if the 2 entries are equal to each other. Okay, so like in this final round of FRI, like what the verifier does is like rather than the prover committing to two numbers, right? Instead the verifier is like, hey, prover, I know if you're honest, these two numbers are the same. So like just tell me that number. So P just tells the verifier, one number, and the verifier, like interprets, the vector in this round explicitly, you know, as that number appearing twice. So let me call this number, I don't know, T final. I don't know. So V interprets like the vector the prover sending in this round as just T final comma T final. Okay, so that's the folding phase. Okay, and yeah, and so what do I want to say? Yeah, so at this point, like the prover was supposed to send these log n foldings of the original committed vector, but or commitments to them. But it could be sending gibberish, right? Like the verifier hasn't done any checks yet. So the final phase of FRI, so let me say the three phases of FRI, at least as I think of them, so there's commit, where you just compute the 2n evaluations of the polynomial to be committed over all 2n's roots of unity or whatever, and Merkle hash, and then you fold, so the folding phase. Okay, and then there's the query phase, right? And the query phase is where the verifier is trying to figure out, like, did the prover actually send these vector commitments to like W2, W3 up to W log n, that were the correct foldings, where W3 is the requested folding of W2, and I forgot to say W2 is the requested folding of the original W, dot, dot, dot. W log n is indeed the requested folding of the previous one, W log n minus 1. So that's yeah. So what happens there is the prover's sending these Merkle hashes, but inside the Merkle hash are these big vectors. So W had length 2n, and then W2 had length. So this was length 2n. This was length n. W3 is length n over 2. Up to W log n, which has length 2. So what the verifier does in the query phase is it says, hey, I'm going to pick, like, I don't know, 128 entries of W, or maybe of W2, let's say. So it's the same kind of consistency check we saw with the column openings in the heroin breakdown. So like you pick 128 random entries. And I'm waving my hands with 128 again, but like, 128 makes some sense if your original message or code word was length 2n. So you pick 128 random entries of W2, and confirm that W2I is indeed equal to R1 times W1I plus what is it? Plus 1 minus R1 times W1 and W are the same. I guess this would be like n over 2 plus I or something. Anyway, the point is that, like, each entry here is supposed to be a sum of two different entries up here, right? And so you're just going to like spot check that that's the case at like 128 random entries, right? And similarly, like each entry of W3 is supposed to be like a combination of two entries of W2. So the verifier is going to pick 128 entries of W3 and confirm for each of those 128 entries that indeed that entry is the correct combination of the two entries of the vector that's twice as long, that was the previous, that W3 was supposed to be the folding of. So you do these consistency checks all the way down, and this gives, so basically the query phase intuitively gives the verifier confidence that the prover actually sent the requested foldings, correctly, that like W2 is the requested fold of W1, and like I said before, W log n is the requested fold of W log n minus 1. And then that combined with the fact that by construction W log n has degree 0, kind of intuitively gives the verifier confidence that W1, the original committed thing, had degree n. Right, like if the prover was cheating, the W1 could have had degree up to 2n. Right, if it was just a bunch of gibberish, the lowest degree polynomial that would have agreed with all 2n evaluations has degree 2n. But if the actual folding procedure causes the degree to fall all the way to 0 after log n folds rather than 1 or more, then well, I guess the degree can't be more than 1. So it's like, yeah, if the original thing had degree n rather than 2n, you know that you'll get down to degree 0 after n folds. And it turns out if the original thing had degree 2n, you would only get down to degree 1 and not to 0. So yeah, that's what's going on. It's like the folding is sort of if the prover is honest, the degree is halving at each step, and unless the prover gets lucky, the degree will never more than halve in each step. And so if after log n foldings you've driven the degree all the way down to 0, that means you must have started with degree n. Because if you start with degree 2n and you never did better than having the degree in each round, then the last thing will have degree 1 rather than 0. That's the intuition about FRI. Okay, I'm going to pause here, and then I will tell you how FRI actually works, because everything I just described is a little bit of a caricature. I mean, it's accurate. All I really waved my hands there was exactly how you go from the verifier's randomness in each round to the folded thing. But I'll tell you the full details after I pause for questions.
Cool. One first question is like how so we start with the n roots of unity, and then when we do this thing, we now have n over 2 roots of unity, or like n over 2 things, or how are we picking the new kind of basis?
Yeah, great question. So let's see. This is exactly what I wanted to cover next. But let me just get the right fact here. Great. So fact, if x is an nth root of unity, then x squared is an n over 2th root of unity. Okay, and this is easy to see. It's like if x to the n equals 1, then x squared to the n over 2 also equals 1. So x is an nth root of unity means x squared is a n over 2th root of unity. And so what is going on is if I take all 2nth root, so I'll say the map x to x squared is what's called 2 to 1 on the nth root to unity. Okay, so it's like minus 1 is a just as an example, right? Minus 1 is a second root of unity, and so is 1, and so is 1. But if I square the two, I just I get out 1, right? So it's like if I give you like all of the nth roots of unity, and then I square them all, what I wind up with is a set of half the size. So maybe I shouldn't have vectors here. Maybe that's just going to confuse things. So if S is what we call all nth roots of unity omega n, and then I look at the set x squared for x in omega n, what I get out is a set. Let me call it S prime. S prime has size half the size, and it's a subset of S. Okay, so that's what's going on is, W is like all evaluations of P over the two nth roots of unity. W2 is all evaluations of, something else derived from P, which I'll give the details of soon, over the nth roots of unity. And that is a subset of the two nth roots of unity. So, and yeah. And then W3 is, all evaluations of another polynomial over all n over 2th roots of unity. And that those n over 2 points is a subset of the n points, above. And so forth. Was that a clear enough answer? As I tell you how the folding procedure actually works, everything will become even clearer than this, or much clearer than
Yeah,
this.
for sure.
Okay.
Yeah, for sure.
Great.
That's all for questions.
Okay, cool. So now I'll tell you how it actually works, how the folding procedure works. Okay, so let's say P is the committed polynomial. It has degree n. So what we do is, remember I said, we view P as like a vector W, which is just, 2n plus 1 or whatever evaluations of P, and we split it into two halves. And then we munge the two halves together. Well, I'm going to tell you now exactly how that is done since I waved my hands before. So what we do is we split, what are the left and right halves? We call them the even half and the odd half. So write P of X equals QE of X squared plus X times Q odd of X squared. So let me give an example. Let's say all my Q's in my notes, I'm going to have P now. Let's say P of X is 1 plus 2X plus 3X squared plus 4X cubed, just as an example. Then P, the even part of X would just be to take the even degree coefficients and only pay attention to them. So we get 1 plus 3X. Now note, I have the coefficient, but the original thing had 4 coefficients. P even only has 2 coefficients. But so, the powers of X in the even part of P reflect that, the P even has half the degree of P itself. And P odd of X is, now let me change the color to blue. P odd of X. We're going to focus on the odd powers here. So powers 1 and 3. So this would be 2 plus 4X, right? And you can just check that, if I look at, PE, maybe I'll switch to red here. PE of X squared plus X times P odd of X squared, this is 1 plus 3X squared, because the X here is X squared, X is getting filled in with X squared, and then plus I guess it'd be 2X plus 4X cubed. And what's happening is this X is getting filled in with X squared, but then so this becomes like 2 plus 4X cubed, but then it's multiplied by X, so you get 2X. Anyway, you see go and check the algebra on your own, but that's we're just like kind of splitting P into kind of the even powered coefficients and the odd powered coefficients, and then treating each of those coefficient vectors as a degree n over 2 thing instead of a degree n thing. Okay. So that's what it means to split P into its even part and its even half and its odd half. And that's what this, splitting W into two halves really meant up here. And then the fold, when the verifier picks, R1 from the field, the fold of P, which was this munging together of WNL and WR, which I called W2 before. What that's defined to be is just, make sure I get this right. P. So let's give this a name. P2 of X. So P2 of X is, or maybe I'll call it Z, my notes call the variable Z here. So P2 of Z is just P even of Z plus, no, I guess I did call it, I'm sorry. Yeah, P even of Z plus R1 times P odd of Z. Okay, so here the R1 is determining, the coefficients in this random, this is a random combination of PE and PO. Okay, and what we're doing is we're just intuitively, we're setting this X here to the random value R1. And then we're kind of replacing the X squared with Z. So this is how you kind of fold the degree n thing P to get a degree n over 2 thing, fold P or P2. Yeah. So it's like PE and P odd have half the degree of P. And now, we're just taking a random combination of P even and P odd, where the randomness was just selected by the verifier here. Yeah, that's the fold. That's the fold. Okay. Okay. And then questions about that fold.
There was a quick question about like what is Z, and is it just X squared? We're just kind of using a different variable.
Yeah, I just wanted a different variable name here. Yeah. So yeah, if we keep with big X, well then this folded thing is just P even, at whatever we're calling the variable plus R1 times P odd, for whatever we're calling the variable. So it's just a random combination of P even and P odd. Yeah, so it's just P even plus R1 times P odd if you just don't want to write the variable because it's confusing. Okay. And so yeah, and so the original commitment was, like 2n plus 1 evaluations of P over 2n through to unity. And so then the folded thing is, the vector of, n plus 1 evaluations. Again, maybe I don't even want the plus 1. Apologies. I'm terrible with univariate polynomials. I make off by 1 errors all the time. N plus 1 evaluations of P fold, which I guess now we're calling P2, over n through to unity. Okay. And so, yeah, and that, so and I will tell you momentarily, I had said previously, right, for the query phase, like each entry of, P fold or P2 is supposed to be a linear combination of 2 entries up here. And so I will make that explicit momentarily, what these, exactly how that works. But that's how the folding actually happens in FRI. And then so when you go to feed P2, you would write P2 as a linear combination of P2 even plus X times, I guess that's of X squared, plus X times P2 odd of X squared. And then you would define the fold of P2, which I'll call P3, as P2 even plus R2, which is chosen by the verifier in round 2, times P2 odd. Right. And so then the prover would commit to, n over 2 plus 1 evals of P3, which is supposed to be the folding of P2 now over the, n over 2 through to unity. And so on and so forth. So yeah, so the last thing I just want to tell you is, exactly how is each entry of, P2, which is supposed to be the folding of P, a linear combination of 2 entries of this vector up here. So let me go ahead and do that. So recall, P, the way the folding proceeded was we wrote P as, P even of X squared plus X times P odd of X squared. The folding, so let me call it P2 of, I guess, I'll go back to Z, is just Q even of Z plus R1 times Q odd of Z. Okay, so that means, the following. Again, I'm just deriving exactly how each entry of this vector here is a linear combination of 2 entries of the vector up here. So let x and minus x be, two nth roots of unity in the field. Right. You remember I said like the squaring map is 2 to 1 over the nth roots of unity. Well, this is exactly how it's 2 to 1, right? Like if I square x, that's the same as squaring minus x, right? So these are the two these are the two things that sort of get munged together when you do squaring, right? For each kind of x that's going to live another round, there's a minus x which is going to go away because when you square it you get x instead of minus x. And so if you so what we want is this folded vector here is like contains all evaluation. Like we want, right, p2 of x, for all x that are gonna survive as a n over 2 through to unity instead of or whatever, an n through to unity instead of a 2 n through to unity. So in omega n, so yeah, right. So anyway, so you can look at what p2 is. So let's look at what p2 of x is, right? So p2 of x is I'll try to. It looks like a little nastier than I expected. All right, I'm just going to write out what my notes say, and then we'll figure out why that's the case. So apparently, p2 of x is r plus x over 2x, the r times p of x, plus r minus x over minus 2x of p of minus x. Okay. I will go and verify that this equality holds in a second, but let's just believe me for a moment. This is telling you exactly how to compute each entry of the folded vector, this thing, as a combination of exactly two entries of the thing you're folding, right? P is the thing you're folding, P2 is the folded thing. This is saying, we need to evaluate P2 at all nth roots of unity. And for each nth root of unity x, the way to get p2 of x is to look at p at both x and minus x, and just take a very simple combination of those two entries. Okay, so this is actually how FRI folding is done. Is you just go over each of the nth roots of unity x, and you set like the first entry of this vector to be the combination of two entries up here. If this entry is indexed by x equals 1, then the entries up here taking the combination of are 1 and minus 1, right? And so you look at p of 1, in this exists. So p2 of 1 is there's some combination of p of 1 and p of minus 1. And what is the coefficients? Apparently it's r1 plus 1 over 2 times p of 1 plus r1 minus 1 over minus 2, times p of minus 1. So that's it. So that's how folding, you can see it's like, for every entry of p2, it's just, two multiplications, and one addition, yeah. And okay, so let's try to verify this. Hopefully I can figure it out on the fly because my notes don't say it, but it should be pretty simple. So I think and I remember how this goes. Okay, so if I okay, so let's look at the definition of P2. Remember, let's treat R1 as a variable, right? So then because P2 is QE plus R1 times QO, right? That's a degree 1 function in R1. Okay, which means if I so let's fix z z to x, because that's like some nth root of unity we care about p2 of x, and so then this became x, and this became minus x. Oh shoot, yes, that's not what I wanted. sorry, I'm bumbling this a little bit. Okay, so the definition of P2 is a degree one function in R1. Okay, which means any degree one function you can interpolate from just two evaluations, right? So if I tell you what so let's call this function like P2 of x, for whatever x we care about right now, is a degree. We fixed x. Now P2 of x is a degree one function of R1. Okay, which means if I evaluate this function at two points, I can actually, because any line is interpolated by two. If I give you 2 points on the line, the whole line, right? So P2 of x is like, if I write it as a function of R1, it's a line. Yeah. So I just need to look at like what is P2 of x for like two different values of R1. Okay, and if I give you those values, I can figure out what P2 of x is, for the our value of R1 I care about, which is whatever value came from the verifier. Okay, so let's consider like P2 of x when R1 is in fact equal to x and when R1 is equal to minus x. Okay, well, let me just clear up some space here. Although I just erased the definition of P2, unfortunately, so I'm going to write it back in a second. Okay, so when R1 equals x, what we had was P2 of x was Q even of x squared plus x times Q odd of x squared. Okay, but I keep going because my notes say Q instead of P. Sorry. Okay, but this is literally equal to P of x. And then similarly, P2 of x when R1 equals minus x is PE of x squared plus minus x times P0 of x squared. And this I think is this is P of minus x. So what I've done is I've written this is all I know. I did a horrible job presenting this because I talked about like fixing x and then setting R1 to two different values, one value being x and one value being minus x and everything. But basically, I know when R1 equals x, I know I have this value. So really, it's like x. I have this degree one thing where x maps to P of x and minus x maps to. Okay, I'm totally botching this. Doesn't make sense that they would both map to. Okay, I'm embarrassed myself here. I want you to just take my word for it that I gotta just stop digging the hole. That this is a valid expression for P2 of x. It only depends on P2 of x only depends on P of x and P of minus x, and that way you can get that's how the prover in FRI in linear time manages to compute the folding of P from P itself. It just goes entry by entry through the folded thing and looks up two entries of the unfolded thing and takes a combination of the two. And apologies that I botched the algebra to actually.
Okay.
Sorry. I'm going to stop digging the hole here. Okay, so that is basically FRI. Yeah, I mean, yeah. So yeah, hopefully, yeah. I guess it's not worth belaboring that anymore. I will briefly sketch the security analysis, or just a key fact here, which this is similar to how I wave my hands like crazy sketching the security analysis of the heroin breakdown because they go through the same facts. So the key fact is what's called a proximity gap for Reed-Solomon codes. Okay, and this says if I have like two vectors like UL and UR. Okay, so these are just two vectors in field to the n or whatever. Okay. And say I look at like a random linear combination of the two. So I don't know, UL plus R times UR for this chosen at random from the field. Okay. So this proximity gap result is trying to understand how far will this so think of this as a folding of UL and UR. So the question is like if one of UL or UR is far from any code word, from any degree degree n polynomial, will this random linear combination of UL and UR also be far from any degree n over degree n polynomial or whatever? And the answer is it turns out to be yes. Like that's the key. So so let's say UL is delta far from any degree n over 2 polynomial. Okay. So with overwhelming with probability at least you normally see things like n over field size, 1 minus that. A random combination of UL and UR is also delta far, at least delta far from any degree n over 2 polynomial. Okay, so I think of this, and I think I said this when we covered the Heron breakdown. I think of this as like any bad apple, one bad apple, spoils the batch, right? So it doesn't matter if one of UL or UR is bad, is not low degree. Then when I take a random linear combination of them, the result will also be just as not low degree. Okay, and so intuitively, this gets applied in FRI because, like, if the prover was lying, right? Remember in my caricature, like every fold splits the committed thing into two halves and takes a random linear combination of the two halves. So in my caricature, this was like WL plus R times WR, or I think before I had R and 1 minus R, but none of it really matters. And the point, like if the prover was lying and the original committed thing was not close to low degree, then at least one of WL and WR is also not close to low degree. And then when you take a random linear combination of the two, this proximity gap thing says, well, this will also not be low degree. And so that not be low degree property is very likely to persist across all the foldings. So if you started with something that's kind of far from low degree, then this folding, the first folding should be far from low degree. So then when you split that into two halves and combine those two halves, that should be far from low degree, and it persists all the way down. And that's why if you start with something that's like degree 2n instead of n, the final thing will, with overwhelming probability, be degree 1 rather than degree 0. Okay, that's kind of the intuition. And so that what that says is like the FRI prover, the proximity gap tells you that the FRI prover is very unlikely. So probability at most, like degree over field size, to get what I call like a lucky fold, lucky for the attacker, right? So a lucky fold would be a fold where the degree of the committed thing, of the latest, committed, folded vector falls by more than a factor of 2 via fold, right? Like if the prover is sort of honest, then every fold should have the degree, and the proximity gap tells you that unless the prover gets really, really, really lucky, none of the folds, right, will more than have the degree, right? So by lucky I mean the verifier picks a random R, in each round to determine the fold, and unless the prover is really lucky, the fold will never cause the degree to fall by a factor more than 2. And that, and if that never happens, then if you start with degree 2n, then you'll wind up with something of degree 1 rather than 0 at the end, and you'll have an issue, right? So there's sort of two ways for the prover to get lucky. right? Two ways to successfully attack FRI. So one is, so attack means you started by committing to, a high degree thing, but then somehow you pass the verifier's, queries. And so one way is to get a lucky fold, where, it causes the degree of the vector, that you're folding to fall by a factor of more than 2. And the proximity gaps tell you that's very unlikely to happen. The other way is to get lucky queries. And what this means is you commit, to you, the attacker, commit to something that's not a fold, the right fold. That's not the requested fold. So there's an inconsistency, right? But the verifier only spot checks consistency at 128 points for each fold, and so again, to summarize, the two ways to cheat are either you get a lucky fold and it causes a degree to fall faster than it should, so you wind up with something degree 0 at the end when you shouldn't have, or you don't actually send the right foldings. Okay, if you don't send the right foldings, you're very unlikely to pass the consistency checks. So that's what the queries are for. That's what the consistency checks are for. So we do 128 of these queries to make that probability 2 to the minus 28, 128 or something. Okay, so that's how to think about FRI security. Again, so what you always see the soundness error of FRI as having two terms, right? There's the probability of getting a lucky fold. That always looks like n over field size. Oftentimes some other factors here coming in from, issues with Reed-Solomon list decoding or whatever. So just don't worry about this. Plus some other term. And that other term always looks like something like 1 minus delta to the number of queries. And this is the probability, excuse me, that the prover doesn't send all the requested folds, but none of the queries detect the inconsistency. Okay, so whenever you look at FRI, you'll see these nasty expressions for soundness error, but this is how to get rid of the nastiness in your head. They're just two terms. One is the probability you get a lucky fold, and the other is the probability that the prover doesn't actually send all the requested folds, but nonetheless, none of the queries detect the inconsistency there. Okay, so that is soundness. Any questions about that?
Yeah, one coming. Copy that speech.
One's coming. All right.
Yes. So can you hear me?
Yep.
So I just wanted to ask: does it matter how verifier picks 128 queries?
Yeah, great. It does. So yeah, let's discuss this. So how do you determine the number of queries? Okay, this gets into these conjectures I mentioned, where there's a difference between how many queries we can prove are sufficient in the interactive setting and how many queries people think are sufficient just based on the fact that there's kind of only one attack known. And they think that attack is truly optimal, but don't have any support for that besides basically that we don't have anything better. Okay, so let's think how to think about this. So remember I said that we had a degree n polynomial, and in committing to it, we Reed-Solomon encoded it, and the commitment was the Merkle hash of that. And here I've been saying the Reed-Solomon encoding was length 2n. Okay, well, this 2, it doesn't have to be 2. This 2 is called the FRI blow-up factor. Okay, and if there's a trade-off here, right? Like if you replace 2 with 4 or 8 or 16, the prover gets slower and slower and slower as you make that blow-up factor go higher and higher and higher. But then the number of queries needed goes down and down and down, right? So it's a proof time versus proof size trade-off, because every query comes with more Merkle authentication paths, added to the proof, and those are full of hash values that the verifier then has to do all the hashes and stuff. Okay, so 2 was just like kind of the low, the simplest, smallest choice of blow-up factor. It gives the fastest prover but the biggest proofs. Okay, and so what's happening is, let's say when the blow-up factor is 2, people conjecture there's no proof of this. People conjecture each query gives 1 bit of security, right? Which means you need 128 queries to get 128 bits of security. And in general, this is log. What they conjecture is it's log blow-up factor, right? So if you set the blow-up factor, this is conjectures. So if you set the blow-up factor to 8, for example, then each query is conjectured to give 3 bits of security. And here people are just like ignoring this term. They're often people often today work over like 128-bit fields, even 124-bit fields. Some projects use, and so if you're committing to something of degree more than 2 to the 24, like this is actually kind of a problem because like 2 to the 25 over 2 to the 124 is it's under 100 bits of security, which is like not enough really. So that's one way people are kind of aggressive, but this whole number of queries thing is meant to focus on the other term in the soundness error and get enough, make this term small enough for good security. And yeah, so the deal is under the conjectures, everybody kind of deploys FRI using every query, gives you log 2 of blow up factor bits of security. So if you want 128 bits of security and you have blow up factor of 8, I guess you need it's 128 over 3 queries. What is that? 42 queries or something. So that's how to think of it under conjectures. I think under what's provable, what's known, is actually I think it's like log 2 of blow up factor over 2, roughly, approximately. And so the gap between the conjectures people deploy FRI under and kind of what we can prove in the random oracle model or run interactively is a factor of 2 in proof size. So so using the conjectures instead of like what we can actually prove, again, either in the interactive setting or in the random oracle model, buys you a factor 2 reduction in proof size. And of course, my view is this is not a good trade-off. That you should just have twice as big proofs and not base not risk that you get totally owned because your conjecture was too aggressive and turned out to be false. But everybody's going to make their own decisions about the right trade-offs between conjectures and performance. So that's how to think about the number of queries. Was that a clear enough answer?
Yeah, totally. But I also wanted to dig deeper into. Let's just get back to the definition of query. Is it only query to the first polynomial, or at any different at any given fold of this polynomial, like at any at any given level?
Yeah, it's every level. Yeah, and that's why. So so basically, you have to make order lambda queries if you want lambda bits of security, and the hidden constant here is determined by the blow up factor. So the hidden constant is exactly like 1 over log 2 of blow up factor is the hidden constant. So you make order lambda queries. Remember, there's log n foldings.
Mm-hmm.
Okay, and any so this means, for each of the log n foldings, we have order lambda Merkle authentication paths. And that's why you get order lambda log squared n total calls, total proof size, right? Because, so it's lambda queries, log n foldings, and each Merkle authentication path has length about log n.
Oh, yeah, I get that. Yeah. So now it's totally clear. Thank you.
Yeah, that's a great question. Yeah. And I'm pretty sure like Stirrer, the reason it's able to shave off something close to a log factor asymptotically, again, concretely, it doesn't seem to yet be a significant improvement, depending on parameter regime anyway, is that they basically make there be like kind of less than log n foldings. So it's like, I think the first folding, I think there might be only like log n foldings or something. Like they're able to just kind of reduce the size of the committed vectors so fast, and there's so few of them that, like kind of you save this log factor that, feels like it shouldn't be needed, but, is there in FRI, where every single one of the log n foldings produces, lambda authentication paths, each of size log n. So if you have, fewer you constant, log n foldings instead of log n, you can maybe save that or something.
Sounds great.
Yeah. Okay, more questions?
Can you go into more detail regarding what a lucky fold means or what that looks like?
Yeah. So that's just, you've committed to, this thing, some length L, and it has degree, D. So length L, degree D, in everything so whatever L and D is, it hardly matters. And so what I mean is, like, if the prover is honest, then for any fold, when you fold any fold, meaning the randomness, right? We split this into two halves. You pick a random R. You set this to some WL plus R times WR, whatever it is. Call this W prime. For if the prover is honest for any fold, the degree of W prime will be D over 2, and the proximity gap says, with overwhelming probability, basically, I'm waving my hand, I'm being imprecise here because really we have to talk about distance from degree D and, so forth. But just keep it simple. The proximity gap result says, so if the prover is honest, the degree of W will be at most D over 2, and the proximity gap result says, with overwhelming probability over the choice of R, the degree of W is at least D over 2. So a lucky fold is where, like, you have, some degree D thing you're folding, and somehow, through the verifier happens to pick a choice of R where the folded thing now has degree, significantly less than D over 2. Right. Or even just a little less, so that's what I mean. So it's like, look, what's the worst? The maximal cheating prover at the very start will commit to a degree 2n thing, right? Like that, just gibberish, committed to gibberish. So the gibberish has degree 2n, but it's claiming it has degree n. Okay. Now imagine, the verifier folds, chooses the fold for that thing, chooses an R1. Imagine that, while we started with a degree 2n thing, imagine the folding of that degree 2n thing was magically not n, but rather n over 2, right? So we should have had a halving in degree, but we got a factor 4 reduction in degree. If that happens, the prover wins. The prover's good, right? Because now the folded thing is the same degree it would have been if the prover was honest, and then you had a halving. Yeah, so that's what I mean by lucky fold. It's like the verifier picks some randomness so that rather than the degree, falling by a factor of 2 from the fold, it actually falls by a factor of 4 or more. If that ever happens, the prover wins. It can just be honest from there on, and everything is great. And so, that's what I mean by lucky fold. Is the degree falls too much, more than it should in a single fold. Does that make sense? Did that clear it up?
Yep. Can you? The next question is about WER, and specifically, how do verifier costs get improved?
Yeah, I'm not going to be able to say that in detail off the cuff. So I'll just punt it.
Cool. Yeah, no other questions.
Okay. Okay, great. Yeah, I guess the last thing I'll mention is, like, when you fiat Shamir this stuff, like there is an attack known. Now it's like a trivial one. It's the one that, yes, I just want to mention the attack, I guess, right? And yeah, I mean, people know this attack exists, but I want to make sure this attack exists, right? So this is like the best known attack on FRI. This is the attack that everybody conjectures is like exactly optimal. Okay, so let's say the prover commits to some W, and it's just gibberish. So right, like it had length 2n, degree 2n. Okay. And now let's say the verifier goes and requests a certain folding of W. Okay. And so, the prover is supposed to send, WL plus R times WR or whatever. And the prover is like, I'm a cheater. So I'm not going to send actually WL plus R times WR, right? I'm just going to send some degree n thing. Okay. And let's actually say, let's say the degree n thing is the following. I don't want to get that. Well, does it matter? Yeah, it does matter. Yeah. Okay. So let's say, how do I want to do this? Sorry. So that, okay. The prover, if the prover hadn't cheated, this would be a degree n over 2 thing. Okay. So let's say this is a degree, this is a degree n thing, because it's not a lucky fold. If so the prover wants this to be degree n over 2. Okay. So if it was a lucky fold would mean this thing is degree n over 2. It's not. This was not a lucky fold. So the prover's like, okay, I didn't get a lucky fold. Whatever. What I'm going to do is I'm just going to commit to a degree n over 2 thing. I'm going to pick the degree n over the degree n over 2 thing that has kind of maximal possible agreement with the true folding, right? So I'm just going to pick half of the entries here. I'm going to figure out like what the actual folding is for those entries, right? And I'm just gonna there's a unique degree n over 2 thing that agrees with them. Unique degree n over 2 polynomial, that has the n over 2 evaluations, just for this first half. And I'm going to fill the rest in with whatever that is. So let's call this polynomial, I don't know, Q star. So so what the prover is going to do, it's going to commit to the commit to Q star, and not actually the folding. Okay, and so it basically this thing is low enough degree that it can kind of be honest, for all the subsequent foldings, and naturally, get a degree 0 thing at the very end, and that's great. So basically, the only place this prover lied was the first fold, right? Like the verifier requested WL plus R times WR, and the prover's like, screw that, I'm not going to do that. I'm going to just like look at the first half of WL plus RWR. I'm going to take whatever low degree thing actually, agrees with that half, and I'm going to fill the second half in with the low degree thing instead of actually WL plus WR. Okay, that means that the lying is all in here. Okay, let me make it, I don't know, blue. This is the blue circle is the lies. This is the only place the prover lied. Okay, so the prover will only be caught if the verifier queries the second half of W2, right? The blue circle is the second half of W2. This, yeah. Okay, and say yeah, so that's what this attack achieves. And so what is the probability that all queries are not in the second half of W2? So the second half of W2, so that every single query misses the blue circle. Well, every query is in the second half of W2 with probability of half, right? Every query is somewhere in W2, and then so you're in the first half with probability of half and the second half of W2. So this is exactly 1/2 to the number of queries. Okay, and so yeah, I mean, and this is the attack, and then so if you're running FRI interactively, the success probability, you kind of only get one chance to attack the protocol, and so if you make 64 queries, you'll have a 1/264 chance, if you're the attacking prover, of passing the verifier's checks under this attack. Okay, but with fiat Shamir, it's like you can kind of run this attack over and over again in your head, and you only have to succeed once, right? So the expected runtime, this is called the grinding attack. Basically you kind of, the prover, after think to fiat Shamir, can kind of make the verifier run the protocol over and over again with a fresh random choice of queries every time. And if the prover ever finds that the verifier makes like a choice of queries that don't detect the attack, it has found a convincing proof for the fiat Shamir FRI protocol. So the expected runtime in the fiat Shamir setting is 2 to the number of queries here. Okay, and in general, if you blow it, you see exactly why like the number of bits of security provided by each query is like log to a blow up factor. So the reason what's happening here is every query is giving you 1 bit of security. It's making the expected runtime of the attack double. Okay, and the reason it's 1 bit of security is because the blow up factor is 2, and log base 2 of 2 is 1, right? If the blow up factor was 8, then it turns out the prover in this attack is not able to get like 1/2 agreement with this vector or the right vector. It's only able to get like 1/8 agreement. And so then the probability that every one of the queries lies in the red part instead of the blue part is like 1/8 to the number of queries instead of 1/2 to the number of queries, and that's why the blow up factor is coming in, as I said. Okay, and so yeah, so I don't know, you just need to, the reason I'm saying this is because people are conjecturing that this is literally the best attack possible, and they are deploying FRI configured such that this attack is kind of barely beyond feasible to run. So they might set like 1/2 to the number of queries. They might set the number of queries to be like 100 or something, and so this attack really does take like time 2 to the 100 to run. And it's like, yeah, 2 to the 100 like is not runnable, like it's not feasible to do 2 to the 100 computational steps or whatever today. But if there's an attack that's only like a little bit better, then maybe this falls from 2 to the 100 time to run down to 2 to the 70, and then this is totally feasible. This is very, 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 this is cheap even. Okay, so so it's aggressive, right? Like the known attacks on today's deployments on FRI are not feasible, but they're kind of just beyond feasible. And the attack we're assuming is optimal is sort of like the dumbest possible attack, where the very first fold you're like, okay, I'm just gonna like pretend this was a lucky fold when it wasn't, and just hope none of your queries detect the deviation, the inconsistency. And that's the whole attack. It's like kind of brain dead. So. All right. Hopefully that clarified exactly where this, bits of security per queries is coming from, and, exactly what the, kind of known attack on FRI looks like. And, we think this is optimal, but we don't have too much evidence of it. And yeah. Okay. So that's everything I wanted to say about FRI. So let me just see if there are any questions. And if not, we'll call it a week.
looks like no.
Okay, well, kind of a rough presentation. So, but I hope it was useful. And I think next week it's we'll either do Growth 16 or Recursion and Nova. So I'll just let Abby know as soon as I decide. Those are the last two topics to cover before just like a general kind of overview rehash of the Snark design space, and then we'll be done this run through of the session. Okay, thanks everyone, and I'll see you next week. Yep.
Thanks, Justin. Bye, y'all.
Yep.